Afternoon, everybody. I think we'll get started. Thanks for joining today. We have a multiple time presenter coming back yet again. I don't know if you win the award for most presentations, Geronimo, but I know that you're up there. Um, Jeronimo from Florida International University and AmLight is going to be going over, I think this is a follow-up on a talk that you gave last year on sort of the initial stages of the monitoring and testing framework that you were developing. But this is sort of an overview of what you're doing right now with the work on AMPath, and I think you're going to go over a little bit of some of the results that you got during testing during SC this year. So I will hand it over to Geronimo.
Yes, good afternoon. Thank you, Jason. If there's a prize, I accept money, but I don't think we should go towards that path. This is for those who attended Internet2 TechX. It was the first, like the introduction of this solution was at TechX last year. We everything that we have presented so far, it's kind of a natural path of how things are evolving at AmLight. So we might have touched this subject, but I think a focus on this solution is the first time. So again, I'm Jeronimo Bezerra from Florida International University. I'm the Chief Network Engineer of the AmLight project, also co-PI of the AmLight project. Renata Freis is one of the senior engineers at AmLight is here on the call. So in case you guys have questions, we can work throughout this. And if you have questions, just interrupt us right away. Jason was going to be monitoring the chat. So let's get this started. So the name of the talk is BERToD. I'm going to be calling just BERT most of the time because it's a very famous acronym, bit error testing, bit error rate testing. So this is BERToD is an automated bit error rate testing framework to search for packet loss at AmLight. And same outline as always, a motivation for this work, how the solution works, all the lessons learned and lessons that we're still learning. Everything this is still an ongoing effort. So there's a lot of next steps in conclusion. So probably there will be a follow-up presentation to this one. A little bit of disclaimer. So I want to be a little bit more specific about the kind of error we're looking for. First, let's talk about the difference between packet and frame. When we talked about TCP/IP, we know one is a representation of data from the layer 2, the other one layer 3. But also even in the 802.3 documentation, sometimes they use this interchangeable. So in this presentation, if I say frame, if I say a packet, where I'm representing the idea is to talk about the same data blob. Okay, so there's no difference of layers here. But the main difference that I want to make here is the difference between packet loss and packet drop. Although packet drop could be part of a subset of a packet loss, I want to separate here because in our perspective, when you drop a packet, it's because you intentionally dropped that packet, right? Because you have tail drop implemented in the switch, or because you have small buffers that you put more traffic that buffer can handle, because you have QoS policy, you have traffic prioritization, you have a blocking topology, you have traffic engineering. In all those circumstances here, you drop the packet. That was intentional, was to preserve the resources or was to accommodate the traffic that you're getting. And this can be monitored in multiple ways because it's an implementation. On the other side, loss in a more like generic way here, I'm going to be focusing on loss from the perspective of someone else dropped our packet or something else damaged, corrupted that packet, and there's nothing that we could do it, and it's sometimes extremely hard to narrow it down from outside unless you do like a physical intervention, right? So if you have a damaged transceiver, if you have a dirty fiber, if you have a power outage, if you have a fiber cut, those will be the ones that I'm going to be focusing on and not the things that we have some control. And the reason why I'm separating is because in the past, for those who participated in previous CI lunch and learn sessions, I talked a lot about INT, bandwidth telemetry, and how we monitor those queues, how we monitor the drop. So we kind of know a little bit of how where the drop is, but we don't have the visibility of loss. So this is the reason I'm focusing on now for loss only. And the motivation, I think it's pretty clear for everyone here. Data transfers over long haul links or high RTTs suffer extra when you have a packet loss. No question there. I put some references of a presentation that I showed those numbers as part of a microburst testing presentation that we did. But at AmLight, the RTTs, they go from 125 to 131, depending if you're going to from Chile or Brazil to Internet2 or ESNet. So anything that goes beyond 80 milliseconds, it's already a lot of RTT, and any packet loss is detrimental to the quality of that traffic. So in our case, we realize anything under like one packet out of 1,000 of every 10,000, it's already a lot. So this is the motivation. We want to find those tiny packet loss, but not just under like one out of 1,000. We want to do this because we have science applications that expect better network performance, and we have science applications that demand better performance. We have SLA-driven science drivers. We have a science driver that actually pay for quality with a penalty associated if we don't achieve that quality. And they have a very aggressive mean time between errors and mean time to recover. They don't go specific where's the packet rate that they're looking for, but they said that it has to be according to the 100 gig IEEE standard, which is 10 to the power minus 12. And if you go from bits to bytes, because we're now talking about packets, and that packet that goes like around 1,000 bytes, that's going to be 1 to the power of minus 9. But such granularity is very hard to achieve when we just use the standard hardware software. The tools that we use today are very hard for you to find or pinpoint exactly this kind of bit error rate. And on the other side, our network has grown a lot in complexity in the last 5 years. I'm going to talk a little bit about this in the next slides. But what we understand is when we started this work was that all the solutions that we had at some point, they presented scalability, accuracy, or granularity limitations. So before I talk a little bit about the network itself, let me talk about the program for those who never heard of AmLight. AmLight is a distributed academic exchange point. It's built in collaboration with US, Africa, and Latin America countries. It's supported by the National Science Foundation under the International Research and Education Network Connections Program. It goes from 2021 to 2025. And BASIC is a collaboration with among all those partners that you see here on the right side. And each one of those contributes something, either money, either people, either collocation, either equipment, either link. They contribute somehow with resources that we could use and build this topology. So this effort here is not a product of just one person, one group working. It's a collaboration. And the same goes obviously for the network configuration. So currently we have 3,900 gig links, 2.1 terabits of international connectivity. By the end of this year, we have a big upgrade to do it. So we're going to have more than 5 terabits of total capacity, total meaning international and terrestrial local connections. We use a variety of technologies, dark fiber, spectrum, optical waves, lit services. We have 9 sites, 19 racks from the US, Brazil, Africa, and the Caribbean part, and all the way to Atlanta, Jacksonville, where we meet Internet2 and ESNet. We have 20 programmable switches in production, 5 Juniper routers. We have 10 gigabit per second nodes. We have 400 gig nodes that are dedicated just for testing, simulating traffic, simulating applications. 4 in-band network telemetry collectors that we talked about this before. And today we generate around 10 million packets per second of telemetry, 96 terabytes of telemetry per day. So in terms of what we do pretty much everything to try to monitor the network, right? We use the counters from the SDN domain. We use ping, SNMP, trace route. We do optical telemetry collection. We do INT and JTI, which are streaming based. JTI is for Juniper telemetry interface for the Juniper routers. We have persona measurements. We have dedicated 100 gig nodes, as I mentioned. But all of you that do like troubleshooting of packet loss at some point, you're going to agree that this is still very challenging to isolate exactly what the problem is. And with this comes a very high operational cost, right? So if someone reports that there's a packet loss and it's just one packet out of a billion, sometimes you're gonna have to evaluate the results, try to correlate the data, run tests, send engineers to clean, replace the fibers, replace the transceivers. You're going to steer traffic, you're going to run again, and sometimes you're going to run again, and it's not going to happen, right? So the error is not necessarily all deterministic by the characteristics of the environment. So usually leads to days or weeks of work for troubleshooting. Um, there are a lot of research and education networks here that have packet generators or network testers that they use more like in an ad hoc fashion. So, for example, they buy this to test the links. If there's a new 100 gig link, they use this. They to test like a new switch, a new router, to test ports, to test transceivers. So those packet generators are available, but the community, the way we see it today, they use more in this ad hoc fashion just for specific needs, um, which is disappointing because this has very granular, like it's very granular because it's hardware based. But I understand the way some people use this way. Sometimes it requires a lot of manual configuration. There is a learning curve to read the results and understand the results that the packet generator provides. So this is where the BERT or bit error rate testing on demand software came, right? So we tried to create this framework that would connect with all the data that we get from INT, all the data that we get from the SDN controllers, all the possibilities that we can do in the switch with the P4 programmable pipeline, and the traffic generator that we have, which is hardware based to detect BDR rates as low as possible. In this case, we're aiming for 10 to 1 to the power minus 12. So we leveraged all those results that I mentioned. But either way, even with all of this, everything being based in hardware, we trust the hardware, but it's still near deterministic. It's very close to deterministic, but it's only going to be deterministic if all the network is available just for you to test, right? If you have anything else that shares the resources, at some point, there's going to be competition. And that's where those drops come that I was talking before. But either way, we still have like very highly accurate and granular results. So before I go any deeper into the solution, let me go through some concepts for those who never attended those INT presentations, SDN presentations before. So traffic generators, this is a very standard commodity off-the-shelf product. It's been out available for the community to purchase, and since internet became a thing, this is how the carriers test the infrastructure. That's how the carrier run an evaluation of a link to see if the link is ready to start billing, right? And they usually connect those. They have the portable units like the one you see here on the bottom that they carry. They connect to the data center and leave it running for 72 hours. And then if the tests come clean, then they consider delivered to production. So if you had the chance to go to data centers and you probably saw some of the racks with those units running tests maybe on the bottom, maybe one shelf, but it clearly shows that this is a temporary thing because it's a mobile unit. So those traffic generators, they do everything in hardware to achieve those great results, deterministic results. Everything has a dedicated ASIC or FPGA. They're very flexible in terms of creation of those packets. Depending what you want to test, there are packet generators that can even test BGP sessions. There are packet generators that can test OSPF with scalability. There's one that can test applications, so you can customize the packet, size, headers, number of packets, packet rate, duration, and even payloads, as I mentioned before. All of them have user interfaces and APIs for remote integration. And going back to the presentation we had last week that Cody was leading about the WAN experience, we talked about SC23 and 24. In the last 2 years that I participated, I know that those are the vendors that provided the equipment, and we had the chance to play with all of them. So thank you to Expo, Yavi, and Keysight if they're here on the call, but those are all great products that we use every year. And they helped a lot for AmLight to learn about those boxes because we got training, we got exposed to them, and we got to test a lot of links. So the one that FIU purchased some time ago is called the Expo FTB Net Blazer. It has two slots. It has a total of 400 gig ports. It has two modules, each module with 200 gig QSFP interfaces. We separated that one module is just for experimentation, so it's connected to a test bed, and one module is connected to production, that's connected to BERT. As I mentioned before, these guys, they have APIs. Usually there is a standard, it's called SCPI, SCPI is an API, is standard commands for programmable instruments. This API is no fun. So what we did, instead of leveraging it directly, we create like a Python library that can be used. There was a lot of support from Expo for that. So we create this library that we instantiate everything in Python, just like we do normally, python.start test, and then it sends a lot of commands and validate those commands. So this was the first step because this is how BERT interacts with the package generator. And the solution that we purchased, this one, has two main applications that we use. Has the EtherBERT, which is testing for the Ethernet layer, and it has MonGen or Gemmon. I think it's Gemmon, probably misspelled. Is generate packets, and then you can customize packet with a lot of flexibility, but then it doesn't focus necessarily in bit error, more like in a packet error rate. So for the EtherBird, there is there's a math. I would say there's a computation. It's called PRSBS31. Is pseudo-random bit shift 31. That is the more accurate way for you to test the bit quality of any frame because it leverages the last 31 bits to compute the next one. So it's very accurate and goes back and forth. So it tests a packet from the beginning to the end and the end to the beginning. And this is the most accurate way for testing for bit errors. But they have other solutions like they do RFC 2544 that everyone knows is for testing network equipment, and RFC 6349 that is for TCP, but for commercial. The other technology that I'm going to be talking about is INT. I'm not going to go deeper into this, but picture that INT is a telemetry per packet. It happens directly in the switch, doesn't involve any CPU. It's not like S-Flow or IP-Flow or IPFix or NetFlow that have to go to the CPU of the box. This has zero impact to the switch, and then it gives us the flexibility of testing and monitoring every single packet. Every packet is copied without the payload, but with telemetry to a telemetry collector. So that means that we have a lot of scalability, and that's the solution we talked about, 10 million packets per second. And with INT, you have this kind of visibility. You can see the queue occupancy that helps us to troubleshoot jobs, right? So you can see on the left side, on the top left side, a normal queue occupancy of 30 kilobytes. And then on the right side, the congestion, we have 1.5 megabytes of data on the queue waiting to be serialized out of the interface. On the body, you see what's the normal hop delay or the time that it takes for a switch to forward the packet when there's no congestion, like 2 microseconds. And when you have congestion, that goes all the way to 60 milliseconds, right? Almost like 5 times, 5 degrees of freedom here. Our SDN helps a lot. The solution that we built is a homemade SDN controller. It's called Ketos. So Ketos has functionalities like any network orchestrator to do topology discovery. And also service instantiation. There's no Mac learning, so you can do a lot of those tests back and forth without concerning about populating FTP tables. And in this topology on the left side is exactly the production topology for all the switches, all the links, all the ports, everything here is accurate. And then on the top left side, you see a black triangle, that's the traffic generator. And connected to every ellipse in blue, it's a circle with a 19 number inside. That's a loop port. They were looping the port 19 with this loopback connector that you see here in the middle and the bottom, right? So we place a loop in every switch. So the SDN controller creates a path that goes from the traffic generator all the way to that loop and back. And that's how we counting the packets that are received back and doing all the math on top of those packets, we realize how much bit error rate we have. Now, obviously, we can only see here, we cannot isolate per direction, right? But for those packets that make it back, then if it's just a bit error, then we can track those. And on the right side is the topology look like a tree, where you go from the root, which is the same switch here, that connects to the traffic generator, all the way to each switch. The idea is to test every link that we have in the topology. So we build multiple branches, multiple trees, that in a way that we guarantee that every link, at least every international link, is somehow tested by BERT. So going back to the main topic, the BERT is a framework. It's not just one tool. It's more like a scheduler that connects to multiple resources and get data and take action, right? So in this case, BERT reads the topology, the policies for testing. So we decide test duration, what kind of application, the packet length, the formation of TCP/IP headers, number of packets, maximum bandwidth, scheduling, all of this, right? So we get everything that is supposed to, all the tests that we want to do it. Then from Ketos, from the SDN controller, we get the topology, we instantiate the path from the traffic generator all the way to a remote loop in each one of those remote loops. Then from the software that we call, this framework that we call Behavior Anomaly and Performance Manager, picture it like a traffic engineering system. We get all the data from the switches, from the optical layer to see which links are operational, which links have bandwidth available to be used, which priority to use, which queues to use. And then we have the packet generator, the EXFO that I mentioned before, that after BERT decides what's going to be tested and how long it's going to be tested and how it's going to be tested, is send these instructions to the generator to generate those packets and push the packet to the network. So we test every link every 30 minutes. Everything that is in red here, those numbers in red, are numbers that we're still experimenting with. So if you don't agree, feel free to share. We're also learning about this. But this is what we have been doing for the last, I would say, since September. So we run the tests every 30 minutes. We test for latency. We test for jitter, frame loss, out of sequence tests. We do that each test for multiple frame size, a combination that we call a mix that tests small frames and also tests that only run at 9,000 bytes. We run each test for 10 seconds. We send up to 500,000 frames. And if the test fails, then we run it again just to make sure that it is something that is deterministic or not. So we tested it again, multiply by 3. So then we run for 30 seconds, 1.5 million frames, and then we stop there. If it still comes back with the error, we stop there. If it doesn't, we stop there anyway. But at least we run a test right away so we make sure it's not just a flat. It's not just like a hiccup that happened. The choice for bandwidth. Usually when we test a link, right, when the carrier provides you a new link, you test for 100% of the capacity. So if you get a 100 gig, you test at 100 gig. This network is in production. Those links are in production. So we need to see how much bandwidth is available. And then we aim for no more than 50% of that bandwidth. Or if the whole bandwidth is available, we try to keep under 40 gigs. Okay. So I know a lot of the tools out there are not very accurate to provide bandwidth utilization, but that's why we use INT. So INT, you have per packet telemetry, so you know exactly how much bandwidth you have for the past like 10 milliseconds. So this is why we trust those results. We display the results for multiple different ways. So that's just Grafana, playing with Grafana. But we also save everything in a text file. And I'm going to talk about this later because we're using this for learning, dynamic learning. We use Grafana annotations. So this is one of the things that we always wanted to see is like if you have errors and you have a display of errors, and then you know why, or if there was a change to the network, there was a link that flapped, anything that happened, we submit the annotations to Grafana, and then we can export those annotations later. So that means that if you see a change in the graph, there's going to be a line saying, oh, look, this happened at that time, and maybe that's the reason. So we're going to see examples throughout the presentation. So this is the granular results, like when you run the test for the last an hour. This is what kind of interface you have. You have frame loss counters, you have frame loss percentage, you have jitter, you have latence, and you have the auto sequence. In this case, for every path. Every path has a different VLAN that we use this as an index to keep track of the path that was used. And then you can see multiple packet size like 1518, 128, 9000, or 0, if that's a combination of multiple packet sizes. So this is great for you to see the last 24 hours. Not very good if you want to correlate events, right? So if you see all those vertical lines here, and then you have, we have 36 tests. There's multiple shades of gray that are of blue here that is hard to see. So unless you're seeing like this black, brown spot here in the middle, everything else is hard to correlate. And that's why we create like historical views, right? So we consolidate the data per day. We just sum up all the loss of that day. And then you have results like this. We tested over time. The same thing is like the maximum number of errors for the day that had more errors. So, there was a day that had 4.79% of that day. So then you start aiming to like how to prioritize troubleshooting, right? And this here is here on the right side, this is the annotation. So if you see this dashed cyan color lines here, you see 1, 2, 3, 4. Those are annotations. It's something that happened. Either it could be like a manual intervention, like someone went and changed the patch cord, or the link went down, or there was a power outage, or there was a visit to the data center. Then this is documented here because we use this to try to correlate events. Yes. So next one. Now going to the most interesting part, the lessons learned, right? So one of the things that is always very polemical, and there was some discussion during the TechX, is like, if you want to test your infrastructure, you don't want to test the user experience, right? So or you test one or you test the other. And when you test the infrastructure, your traffic needs higher priority than the user traffic. So if you need to bump the user out to test it because you want to be accurate about a quality of the infrastructure, you have to do it. Then you do it, right? So what we learned is that we're running BERT as the same priority of every other traffic. And we realized, yeah, that's not good. There was a lot of buffer utilization that was because of that traffic, the burst of traffic that BERT creates, and that was leading to more drops, which is the exact opposite of what we want, right? And also the results were not very consistent because you could never separate between a drop or a loss. So what we did, we changed the traffic prioritization policy, the table that you see here on the right side. So like any Ethernet interface, you have at least 8 queues, right? So this is physical. It comes for every switch has this. Everything at AmLight is Q1, right? So then that includes the traffic, includes the BERT traffic. And at some point we decided we have Q3, that's for Vera Rubin. This is a telescope project. And then we added a Q4 that everything is the highest priority for the most deterministic monitoring that we want BERT to do it, right? So every time we run a test, we run a test in Q4 and Q1. Q4 tests the infrastructure, and Q1 tests the user experience. The Q1 tends to be a lot more, unreliable because there's drops. But to minimize the drops, that's why we use the telemetry, right? So we look at what is the utilization of the buffer, what is the utilization of an interface, and we try not to use more than 50% of the traffic available or the bandwidth available because we know at any point someone can start something. So we don't, those tests are very small for this reason. So this is one of the lessons learned, and I'm going to show you those results before and after in the next slide. Something else is, yeah, I mentioned that both Persona and BERT have the same queue for Q1, so that's how we test the user experience. One of the things that we learn is there's no such innocent maintenance at the data center, right? Um, so one of the things that we learned very early on is that even sometimes when our operators are labeling fibers or they're following fibers, that is enough to misconnect a connector, an LC connector, and lead to problems and lead to specific errors at that moment. Or even like an example on the right, on the side, on the right side here, there was a visit to the data center and someone put a label and touched the connector and start creating errors every day. And then there's an annotation saying here someone went to the data center, and there's an annotation here saying someone changed the patch cord. So what happened was during the process of labeling or following or whatever was done, that connector got damaged, right? And it was not disconnected. It was just which someone just followed the fiber as far as I heard, right? The operators are here if they have a different perspective. But this shows that even things that we thought that those are innocent, right? So just touching a fiber, touching, following fiber, organizing, cleaning, at that moment that you're bending that fiber, that operation is enough to create some packet loss. And sometimes we see those when we go to the data center. Some vendors have very weird policies, forwarding policies in their switch. So this used to be very common in the past, like implementation of a weighted fair queue for some routers. But we see like small frames, they come delivered out of sequence. We're still trying to understand why. It only happens with specific vendors. Uh, but those vendors are not the ones that we have access to the device. We also test the user network here. So we're trying to work with those partners to isolate. But I know some people said, inside the switch, you have multiple buses, multiple lanes. But we're talking about a packet that is always the same and the same size, multiples being sent multiple times. So unless someone is doing a round robin, it's kind of weird that we see this. But as far as we know, there's no impact, and we only see big numbers when the packets are really small, like 68 bytes. So this is what I was talking before, like when you share a queue with the user on the left side of the red bar, and when you don't share because you have higher priority. So you can clearly see that there was a filter now, right? And now everything that comes towards the right side of the vertical red bar, that's actual error, right? Everything to the left side, the left side, it's a no, it's unclear. To the right side is an error because now that traffic has higher priority. I know some of you might say, yes, Jeronimo, but traffic prioritization doesn't has support against what is that, starvation, right? So even if you are operating in the Q4, eventually the switch will scheduler will give attention to the packets in the lower queues. That's true. That's the reason we count the number of packets. We don't send tests for too long, and we monitor the utilization of the buffers before we send the traffic, even in a higher priority. So we minimize the chance of any queue going to starvation because we're placing traffic in a queue above that one. So next steps, right? So there's a lot of things we want to do with this. Again, this is running for some time. This is not something that is very high priority. There's no one dedicated to this. So this goes in the best effort. But one of the things that we thought it would be interesting to show the power of having our own SDN controller is that how can we integrate the SDN controller with BERT in a way that the SDN controller also leverages the quality of the links to make decisions, right? So for example, I mentioned before, when you get a link from a carrier, you run a test for 72 hours, right? And then once you run the test and if it comes back clean, then you start paying because that link is ready. But that link at some point is going to be affected by a fiber cut or maybe a transceiver replacement or a power outage or a splicing or something will happen. and that link is going to go down. It's just a matter of time, right? But then what we see happening, and we do in our case, is that we just took the word of the operator of the fiber that they did the best job, and we don't actually test the link again. Mostly, first, it's a lot of work to test the link again. Second, we can't afford to wait 72 hours to put a link back in production. And third, sometimes you have to go to site, like you have to physically go, and we were distributed across continent, so it's not that simple. But if the SDN controller could let BERT know that the interface flapped, it went down, and now the interface is steady, is stable, but it wants to test it again, we can do it. So that's what we're working towards. The Ketos controller, after interface flaps, waits 2 minutes to see if there's going to be more flaps. If there's flaps, we wait until 2 minutes of stability. After that, Ketos is going to tell BERT to run a test, and we only run for 5 minutes. And we don't run on 100% of the bandwidth. We use the same metrics as before. If the results come back clean, then BERT will set that link as operational or tell Ketos that link is ready. And then the SDN controller will make that link available to all the applications. So that means that layer 2 provision, layer 3 provisioning, whatever application depends on the infrastructure, will get a notification saying, oh, this link is available, you can start using now. This is the kind of thing that you can't do it easily with, or at least disintegrated with legacy solutions. But this is something that we want to have it because it makes sense, right? We have the tools, we have the generator, we have the visibility of the links. We want to make this work. We also want to automate fault isolation. So here is the last, I don't know, 90 days, something like this, back to December, right? And I removed everything that came backlink. So I only show here the days and the paths that had errors. So you see that by looking at the topology that I'm not showing now, but I showed before, the topology, the branches, right? Even with those branches, it's hard for you to correlate what is going on here. So everything above the blue line is links, is tested that was at higher priority. That means like the one that had priority 4. Everything south of the blue line is the one that shares buffers with the users, right? So you can see that sharing a buffer leads to a lot of different results than not sharing the buffers. And the idea now is like, how do we create a system that automate, oh, if there was a fault in this link and there was a fault in that link, the problem is the other link, right? So how do you create connection between these tests? If they share a link, then we narrow it down by that. If they don't share, but something else happened, like the SDN controller had the fault, or there was a link flap, or anything, right? So we have Hadiz here in the call. He's a AI machine learning researcher that is playing with the data sets and all the log entries to try to correlate, because the operators see everything that you guys are seeing. Like you still have to do a lot of manual troubleshooting. We just highlighted there was an error, but we're not saying what the error is in this case, right? So just like any troubleshooting, we still have to go through this. So we want to do this as much as possible. Also, sometimes we have, this is a graph of a buffer utilization that I was talking about, right? So you can see that the buffer, we set a 1 megabyte as the threshold. Anything above that is a problem. And you see that that ran close to the maximum of that interface, which was 2 megabytes for at least 200, 300 milliseconds, right? So is this the cause of any of those issues or not, right? So the idea is, how do we pick all this data that we have from all those layers and try to narrow down what the problem is? So one thing that we are also working on is comparing the results with Persona. We have 10 Persona nodes. We test every link. At every side of a link, there's a Persona node. All of those are dedicated machines. And we have a mad dash, we have the whole game. And now we're trying to see, well, how each one of those see the same link, right? So this is an example. Something started happening on January 14th for the link that goes from Brazil to Miami, or Fortaleza, Brazil to Miami. And then on 24th, the errors disappeared, unknown cause, but we know what we did in the maintenance. We replaced the switch. That means that we moved the link to another switch, and then the problem disappeared. So for a number of days, 7 days, BERT was very consistent in showing there was one error per test, like one frame loss per test, or maybe all the way to seven. And on the day of the maintenance, there was all the way to 138. But with the persona on the same link, we only saw the bump on the day of the maintenance. And I know that some of you might say, oh, but the scale is not very good, 80%. I have here persona open. If we move the mouse over the line, everything else from 14 to 23rd shows zero. So I don't know if it's some sort of consolidation of data, if it's statistics, but we didn't see this. So we're trying to now correlate the data. I know that this scale here, 0.0002%, it might be a little bit more than what we're doing with Persona right now. But this is something that we want to explore a little bit more. So conclusion here, it's a fantastic tool. It's in production since the September last year. It's used daily by the operators. So one conclusion, obviously, having a hardware-based traffic generator enables quick testing with extreme accuracy. It's easy to reproduce. Not necessarily we learned it, not necessarily just because you run the same test again and there was a fault, there was a hardware fault, that you're going to see it again, especially because of dirtiness on the fiber connectors, right? The fiber is on that corner, you're not going to see it. So you have to keep running the test until you start consistently losing losing packets to then start taking action. Because if you see the report, we have one loss in one link last week, you're not going to start troubleshooting for that, right? So it has to repeat, it has to happen multiple times. I want to highlight this here, that it's a great complement to Persona. It's not at all a replacement. If anything could be part of a Persona, if you have a traffic generator, I would suggest you to implement the same solution. You don't need INT for that. You don't need SDN for that. And you can have the P scheduler to use the library, the Python library, and run tests for you, right? You just have to prepare the inputs and outputs. So BERT is just like an application under the Persona framework, because only tests one thing and it has its own P scheduler that could easily be replaced by P scheduler. So this is it. We have 15 minutes. If you guys have questions, if you want to see in production, I can show some of the interfaces. If not, we're good to go. So let me know.
All right. Well, thank you so much, Geronimo. I'd say, yeah, I'd like to see a little bit of it in production, if you don't mind showing while we wait for a couple questions to come in. So I've given everybody the ability to unmute, so you can unmute and raise your hand or type it into the chat room, whatever makes sense, while Geronimo does a live demo.
So I left some windows open here just to make it easy for us. So this is the output right now of all the tests back from December. And this is what I mentioned before, that we start running tests at the VLANs 500. VLANs 500 are the ones that share the buffers, the 400 the ones that don't share the buffer. You see that lately the network is pretty neat, right? There is only, in the last week, there was only one packet lost for the whole topology. There's some filters to help here. That's graph that I showed before. You can tell, I want to see VLANs that have the error above 1 to the power of -2, and then you start, filtering those results, because you don't want to troubleshoot like every packet loss, right? At some point, if they don't start repeating very often, it's very hard. So those events like this one here in the bottom that you see consistent, those are the good ones, right? Other than this one as well. But if you see this path here, VLAN 405, and you go here to this side, VLAN 405 should be here somewhere. Here, this one, this is the traffic that goes from Miami to Boca Raton to São Paulo to Chile. So that pretty much like goes around Latin America, and it lost one packet. let's say, yeah, no, 2 packets. No, this one lost a lot. So this was a problem. If it's orange, that one lost a lot. So probably it was a link flap or I don't know. I don't think we troubleshoot because there's only one annotation here. And this annotation means that Anthony did something on the link. That's the link we're talking about before. So you have, this is the historical view. So it's great for you to correlate events because if you have all those branches here in the Grafana that match those branches that you see here in the map. So looking just for branch one, then you're only going to see the VLANs for branch one. And if you start seeing multiple VLANs failing, that means that it's probably this link, right? Because they share all this link in common. So this is something that happened at the beginning. We had to clean and replace most of those connections in Miami, in between switches. And one thing that we learned with SC, the supercomputing being part of SciNet, it was to use the scopes. So if you don't have one, please buy one. We think that cleaning a fiber cleans the fiber. No, sometimes cleaning a fiber only make it worse. So you have to clean it again and clean it again. Sometimes you have to throw it out. And we want to recycle fibers. It's no good. So if you have those tools, we bought the Viavi that we played with at the SciNet, and we start scoping every connection in our backbone, right? So as you can see, we're very transparent. We're not perfect. So we learned something, we decided, we admitted that there was a problem, and we started replacing a lot of those connections because at the beginning, the branch visibility highlighted a lot of those bottlenecks. So we replaced most of the connections from Miami all the way to São Paulo. And then we start seeing improvements. So then you can, going through the branches, let me see, second one, then you start, you see that this branch here is pretty good. So that means that this link here is probably clean. And as you can imagine, every line here, every box that has like a thick surrounding is a different test. So those numbers are the VLANs that terminate in that switch. That means that if the test goes from the packet generator all the way to the right side, that means that this link here is tested for every test that goes after this switch, right? So that means that this link is tested a lot. And we tested it 36 times. So at least this one, the one that connects to the traffic generator, is tested 36 times every 30 minutes. And that means that that link is pretty clean because there's no error. So this is one of the views. The other view would be for the last 6 hours, right? So one of the things that we have that I mentioned before was like you see the counters packet out of orders, like from 500,000, 82,000 came out of order. Not sure if that's a problem, but it is something that raised a concern at the beginning. The latencies, our network is based on optical networks, and there's nothing shared, so the latency doesn't change. We have the jitter. The jitter is jitter is a buffer utilization consequence. The more things you have in the buffer, more jitter you're gonna have. So it helps us to, let's isolate, for example, the VLAN that I was talking about that we use the test with Persona. So then you can see that there's a different jitter for every time that you have small packets, which is weird because the jitter for small packets is greater than the one for the big, large packets. I thought it was the opposite, but the latest is the same. And then you can go back as long as you want. And this is the maintenance that I was talking about, the use case that you can. We store, we don't do any consolidation of data. So every test result is going to be kept for as long as possible. So if you keep zooming out, at some point you're going to get the actual number. And just because I don't, oh, there's 5 questions or 5 comments at least.
Well, yes, there's a good discussion there about gorillas wearing mittens and touching fiber patch panels. So the question is from Nick. Are there any correlations you observe between loss and specific types of traffic? And if so, what was that tracked down to be? Config or firmware bugs, and what did the investigation involved?
No, specific kind of traffic, no. What we saw was a correlation between I think the easiest one to make an example is the one that Eli was talking about, is data center visits, right? So let's qualify as visits. Those are agnostic to kind of traffic. We haven't seen anything that is traffic specific, but also in our task here, we're just generating packets. We're not simulating applications. We're not running TCP. We just like we send that many packets at the line rate that we decided. So it's always the same traffic. The only difference is that I have different payloads, smaller or larger. But I don't make any distinction. Oh, this is DNS and this. Remember, this is an active test. Those results that you see here is not for my user tests or user traffic. This is for the loss representing the loss of the test that I created. So I don't know if the users are seeing the same thing, but I'm assuming something similar to it.
Okay. And Mark's question is the optical carrier strength on your interfaces monitored? And if so, has a correlation between that and loss been observed?
So we start doing this uh, after an event here. Let me show you. We start monitoring the Sienna, all the data here from Sienna. And then we realized that some days we had this metric here in the wave server. Let me go back more. There was a day that we actually had something that the Q factor of the link was pretty bad. It was in the red zone here. And then the bit error rate was another one. Yeah. So then he's for some reason we don't know what exactly caused that, but the Q factor was very bad, and then the prefect bit error count and the transponder was above the threshold, and then we start seeing this uncorrected counts of block, right? So then we got all the way to 14 million blocks that were not fixed at that point. So I didn't find any error that matched exactly this time frame, but CN exports the data every 15 minutes. So this monitor is every 15 minutes. So it's hard to actually correlate with something. But we're doing this now. We're like monitoring every aspect of the optical network and see if we find if we can correlate events. Luckily for us, the optical network is pretty stable right now, and those errors were fixed by, guess what? Cleaning the fiber.
Always goes back to that.
Yeah, but that was not our fiber at least. Yeah.
But we need to make sure that we put Cody on forcing everybody to clean their fiber everywhere all the time.
Yeah, that's what the WAN team does. That's pretty much all we do is just cleaning fibers, installing, cleaning, and removing and cleaning to install again. That's the reason he presented what is the Pilates, yeah, the Pilates was built way before my time, exactly because I think it was a problem, right? Removing the fiber, disconnecting because they wanted to change the optical path, and then Pilates enables you to do this without removing the connector. So if you, Cody, if you want to add more details, but we're considering doing the same thing here, having some optical switch to help us with some of those activities.
Yeah, I think for any sort of very dynamic data center environment, that sort of makes sense to have the API switching as a patch panel versus doing exactly what you said. So yeah, certainly understood and great results that you were able to present. So let's see. We had Eli is commenting. Is that similar to the old Glimmer glass switches? Yeah, basically, Eli. It's like a I don't even know the right way to describe it. It's just basically an M to M sort of connectivity for optical stuff, and then it has an API and a GUI that's available to it. And we've been using it within Signet to sort of redirect traffic that way versus having to go and physically remove patch panels and things like that.
Nice.
Yeah.
Thanks.
All right, I think we're out of questions. So thank you again, Geronimo, for going through all of that. I'll make sure that I get your slides posted and the video posted. And with that, we are out of talks, at least for the time being. So, homework item for all of you that are listening still, and tell your friends. We're going to need to have a new round of people volunteering to give talks in the later part of the spring. I'm still hammering on a couple of people to come back. In particular, I know that I want Andrew to come back and give office hours for his timing talk that he gave earlier this year, and I'm sure we'll have the persona people come back as well. At least Mark, maybe not Andy, but we'll get a couple people to come back. So hope everybody has a good couple of weeks, and we'll keep you posted on the schedule once we get a couple more talks scheduled.
Thank you, Jason. Thank you, everyone.
Okay, bye.
Bye.
Thanks very much.
Thanks, Geronimo.